Good afternoon. This is Professor Shannon Gracie. We are working out of the Blitzer textbook, Introductory and Intermediate Algebra for college students. So we'll be talking about exponential growth and decay today, and this is section 12.5. So let's go ahead and warm it all up by solving these two exponential equations, and we are going to round to 2 decimal places. Okay, so pause the movie and warm it on up. Okay, let's see how you did. So here, remember you need to isolate the exponential before you evaluate the natural log of both sides. So if I divide both sides by 1,250, I will have e to the 0.065x is equal to, let's see what that is. Clear this out. And what was it? 6250 divided by 1250. And we get 5. All right. So this is 5. Now we evaluate the natural log of both sides of the equation. And remember, when you do that, when you evaluate the natural log of the natural exponential, you get what was in the power. It comes down. So we will get this. And then isolating x, we will have x is approximately, go back to our calculator here, so we'll have 5, on mine I have to hit the number first, and then natural log divided by 0.065 equals, and I get 24 and 76 hundredths. So 24.76. And if you want, you can put it in your set brackets to show that's the only solution. How'd you do? Great. All right. So now with this next one, what do we do first? Good. Divide both sides by 4, and we'll have e raised to the 7x is equal to, I'll just keep this so far, 1,273 divided by 4. And then we will natural log both sides. So we will get 7x on the left side. And actually, let's go to our approximation here. So going back to our calculator, we will have, this clears out, we'll have natural log, so we have to do 10,273. We have to divide that by 4. And then we're going to be doing the natural log of that. Oops, no. Did you see that? That's the wrong thing. So I'm going to get that decimal first, I guess, and then do the natural log. So 1, or maybe I could go, let's do this, parentheses, 1,0,273 divided by 4, parentheses, and then natural log. Perfect. So 7, I'm going to go a little further. I'm going to go to 7.851. 7.851, and then I'll divide by 7. And we'll get x is approximately so if we divide by 7, we'll get approximately 1.12. How'd we do? Okay on solving the exponential equations? Perfect. So next up, we're going to talk about growth and decay models. So one of algebra's many applications is to predict the behavior of variables. So this can be done with exponential growth and decay models. So with exponential growth or decay, quantities grow or decay at a rate directly proportional to their size. So here we go. In your book, we often use, you can have it as f at t is equal to a0 e to the kt. Our book is using this way a lot, where they say a equals a0 e a0 e to the kt. So I'll probably use that one mostly. So now if k is greater than 0, the function models the amount or size of a growing entity. A0 is the original amount or size of the growing entity at time t equal to 0. A is the amount at time t, and k is a constant representing the growth rate. This is all if k is positive. Now, if k is negative, so if k is less than 0, the function models the amount or size of a decaying entity. So it's going to get smaller. So again, A0 is the original amount or size of the decaying entity at time t equals 0. A is the amount at time t, and k is a constant representing the decay rate. So just, kind of a picture of a growth and a decay. You'll have, so this would be like A and T. And so the first model, if we look at it as a growth, decay. So a growth model will have at time 0, so when x is 0, you'll have some ordered pair here. So this would be the ordered pair 0, comma, a sub 0. And then a growth model is going to go, you're going to have something sort of like this, right, where it grows. And it'll look, the equation will be a equals a0 e to the kt, and k is greater than 0. Now over here, if you look at a decay model, you'll have an ordered pair at, again, whoops, it'll be higher probably. You'll have an ordered pair, this would be 0, comma, a0. And this one is going to decay. So it'll go down something like where it goes down towards there. Actually, that's a little shaky. Okay. So then your equation here is still going to be A equals A0 e to the kt. But in this case, k is going to be less than 0. All right? So let's look at some examples. So in the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million, and by 2050 it is projected to grow to 12 million. So they want us to use this exponential growth model where t is the number of years after 2000. So t equal to 0 would be the year 2000. T equal to 10 would be the year 2010. And we're supposed to find an exponential growth function that models the data. So we're not going to write out all the zeros in million. What we're going to do is use the 3.2 and the 12, and with the understanding that this result is in millions. So let's do it. So at t, let's get a different color. At t equal to 0 will be in the year 2000, and a is equal to what? What do you think? What was it? Let's scroll back up. Good. A was equal to 3.2. That's in millions. So you get the ordered pair 0, 3.2. And then if you go and you look at our model, let's see what we'd have. So we in for A, we would plug in 3.2 equals A0 e to the kt, but the t is 0. So I put in 0 for time t, and I put in 3.2 for A. Well, this would give us 3.2 equals A0 times e to the 0. Well, e to the 0 is 1, so 3.2 equals A0. So that gives us, this information gives us the fact that A is equal to 3.2 times e to the kt. So we're getting there. So this is like, your first step to get A0. Now we have more information, don't we? We also know that at t equal to, so now I'm looking at the information that by 2050 it's projected to grow to 12 million. So 2050 would be time equal to 50, and A is projected to be at 12 million. So that gives us the ordered pair 50, 50, 12. So here we go. In for A, we now plug in 12 equals 3.2 times e to the k times, 50. So we need to solve this equation. So we have to isolate the exponential. So divide both sides by 3.2. Let's see what that is on the calculator. So 12 divided by 3.2 equals 3.75. So 3.75 is equal to e to the 50k. Now, we need to evaluate the natural log of both sides. So, let's come up here. The natural log of 3.75 is equal to 50k. Dividing both sides by 50, we will get a natural log at 3.75 divided by 50 is equal to k. So let's see what that is. we're going to approximate it, but we're going to go, quite a few digits just so that we don't throw our answers off. So here we go. We have 3.75. I need to natural log that. And then I'm dividing this guy by 50. So we have a growth rate of approximately, let's go maybe 0.0264. So K was approximately 0.0264. Okay, so our ending model is A equals 3.2 e to the 0.0264 times t. Okay? So we initially used, let's talk about what we did. So we needed to find A0, that was step 1. Then step 2, we needed to find K. And after we found A0 and K, we were able to get our exponential growth model in terms of, A and T. Okay, so now using our model, in which year approximately will the Palestinian population be 9 million? So our model is A equals 3.2 e to the 0.0264 t. So in for A, we're going to put 9. And we probably should have put here in millions. Okay, so 9 is equal to 3.2 e to the 0.0264 t. Again, we need to divide both sides by 3.2. And we'll get 9 divided by 3.2 equals 2.8125. So 2.8125 equals e to the 0.0264 times t. Evaluating the natural log of both sides, we will get natural log of 2.8125 is equal to 0.0264 times t. Dividing both sides by 0.0264, we will have, let's see what that is. So I still have that 2.8125. I'm going to do natural log of that. And then divided by 0.0264 equals, and we get approximately 39 years. Okay? So T is approximately 39. But we have to answer the question, right? So in which year? Remember, that's the years after 2000, right? So in approximately 39 years, which is year 2039, the population will be 9 million. Okay? Okay, so here we go, the second example. A bird species in danger of extinction has a population that is decreasing exponentially. 5 years ago, the population was at 1,400, and today only 1,000 of the birds are alive. Once the population drops below 100, the situation will be irreversible. When will this happen? Well, we need to make our model, okay? So again, step one, let's find a zero. So we have at t equal to times 0, which was that 5 years ago, a is 1,400. So plugging into the equation, we have a equals a0 e to the kt. So plugging in 1,400 for a and 0 for t, we get 1,400 equals a0 times e to the 0. So 1,400 is equal to a0. So now we have this new model, a equals 1,400 e to the kt. So we're getting closer. We now have a0, but we need to find k. All right, so here we are. The other information we were given was today only 1,000 of the birds are alive, right? So today is 5 years from time 0. So at time equal to 5, a is equal to 1,000. So we have a equals 1,400 e to the kt. So in for a, we put 1,000 equals 1,400 e to the k times 5. Dividing by 1,400, we will have, so let's see what we get. When 1,000 divided by 1,400 is approximately well, let's go to 4 digits again, 0.7143. So, is that what I just said? Yes. So that is approximately equal to e to the 5k. Evaluating the natural log of both sides, we'll get natural log at 0.7143 is approximately 5k. And then you divide both sides by 5 to isolate k. And let's see what we get. So that one number should be up there. So let's do, I'm going to clear it. So 7.7143, and we want the natural log of that number, and we want to divide by 5 equals. So approximately 0.06729. So negative 0.06729 is approximately k. All right, so we now have our model. A equals 1400 e to the negative 0.06729 times t. So now we need to figure out when it's going to drop below 100 or be at 100. So the third thing is use the model to answer the question. So we have our model is A equals 1400 e to the, what was it? Negative 0.06729 t. So now we're plugging in 100 for A, and then we're going to find the time where that'll happen. So, dividing by 1400, we will have 100 divided by 1400 equals. So that'll be about what, 0.07143. Is equal to e to the negative 0.06729 t. And then we evaluate the natural log of both sides, and we'll get natural log of 0.07143, and this is all approximate, right? Is equal to negative 0.06729 times t. And so now we divide both sides by negative 0.06729. And we'll have, let's see what we get. So 0.07143, want the natural log of that, and then divided by 0.06729, and we want to change the sign, equals. So I get 39.2, so again approximately 39. So t is approximately 39. So the answer is approximately 39 years after whatever year it was, after the year that the population was at 1400, the situation will be irreversible. Okay? There you go. All right, so the next problem is just sort of playing around to show um, the time it takes for a population to triple. All right, so here we go. In order for an original amount A0 to triple, what do we have to have? So we have A equals A0 e to the kt. So if we let A equal 3 times A0, that will be triple the original. But look what happens. Do you see that the A0s would divide out? So we'd be left with 3 is equal to e to the kt. And then, like we normally do, we natural log both sides. So we would get natural log at 3 is equal to kt. And then dividing both sides by k, we get that t is equal to natural log at 3 over k. So we just showed it. Awesome. All right, so example 4. The August 1978 issue of Natural Geographic described the 1964 find of bones of a newly discovered dinosaur weighing 170 pounds, measuring 9 feet with a 6-inch claw on one toe of each hind foot. The age of the dinosaur was estimated using potassium-40 dating of rocks surrounding the bones. So it turns out that potassium-40 decays exponentially with a half-life of approximately 1.31 billion years. So we use this fact, the fact that after 1.31 billion years, a given amount of potassium-40 will have decayed to half the original. And we're going to show that the decay model is given by A equals A0 e to the negative 0.52912 t, where t is in billions of years. So they just want us to show why that's true. So the first step is to, instead of using time 0 this time, we are going to use info about half-life. And this is going to enable us to find K. And actually, you know what? That'll be the only step because that's what we're supposed to do. So here we go. So basically, half-life means half the original substance. So if you take A equal A0 e to the kt, 0.5A, half of A, 0.5A0 rather, is equal to A0 e to the k times. That happens after 1.31 million years. So the half of the original is half of A0. So again, do you see the A0s are going to divide out, and we're going to end up with 0.5 is equal to e to the 1.31 k. Now, evaluating the natural log of both sides, we get natural log of 0.5 is 1.31 times k, dividing both sides by 1.31, we will get so 0.5 natural log, and then divided by 1.31 equals. So look, we get, if you round to the, fifth place there, we'll get 0.52912 in the negative. So we just showed that K was approximately negative 0.52912. So that's what they wanted us to show in the first part. So, analysis of the rocks surrounding the dinosaur bones indicated that 94.5% of the original amount of potassium-40 was still present. So, we would let A equal to 0.945A0 in our model, and we'll estimate the age of the bones of the dinosaur. So, original model is A equals A0 e to the negative 0.52912t. So, letting A equal to 0.945 times A0 equals A0 e to the negative 0.52912t. And the A0s divide out, so we're going to have 0.945 is equal to e to the negative 0.52912 times t. Then, evaluating the natural log of both sides, we will have natural log at 0.945 is equal to negative 0.52912t. And then dividing both sides by negative 0.52912, we'll have okay, so we get approximately 0.1069. So let's think about what that means. We got T is approximately 0.1069, right? But that's in billions of years, right? So why don't we write it nicer? So we can say the estimated age of the bones is approximately, billion means you know, that's 10 to the 9th. So you'd be moving that decimal over 9 times. So 1069 is 4 times, and then 1, 2, 3, 4, 5, I think. Let's see. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Is 106,900,000 years old. Okay? Okay, so this next skill is actually quite useful in calculus if you're headed that way. So if you have y equals a times b to the x, you can actually rewrite this in the form of y equals a times e raised to the natural log at b times x. So let's just do a couple little examples to see how we change that. I just wanted you to see it. So this one, do you see the a is 1,000 and the b is 7.3? So this would be 1,000 e raised to the natural log at 7.3 times x. And that's the answer. And the second part, a is 4.5 and b is 0.6. So y is equal to 4.5 times e to the natural log of 0.6 times x. Alrighty, so that's it for today. Have a fabulous afternoon. Bye.